Welcome back. We're in the middle of exploring membership in all the ways that it can change as we change the logic surrounding our story problems. In our classical logic, we simply assign things as true and false. It's great for inference, it lets us count the number of subsets and many other tools. However, it might lose nuance. In a computational setting, we might have situations where we simply don't know if something is or is not a member. Today, we're going to explore a modal membership problem. This is where what it means to be a member is not actually declared in a uniform way. It may depend on what situation we're in, the mode of the test. So I have before me a situation in which a web browser is trying to protect the behavior of its users. A user types in a place to go, and it might throw up a warning instead of giving you the web page. How does it do that? There are billions of websites, and on top of that, they each can have thousands to millions of individual files that could be served up. How can a web browser quickly tell us that this is perhaps a malicious page? The actual technology has some of the most exciting names and algorithms, from Bloom filters to hyperlog. If you want to do a deep dive, I recommend Probabilistic Data Structures by Andrei Gekov. Let's see one simple version of how this could work. The key idea is that we're going to try to stack a lot of tests together on one common piece of data. Here's how that might work. So how is our website going to update us on the negative web pages? There's no way for a browser to store a list of all the names of every bad website. That'd be too long and it'd be too hard to search. Instead, we need something that tests membership in a much more clever way. And we're going to use the logical operators or and to hide one of these techniques. It's what's known as a Bloom filter. What we'll have here is that we'll start with individual websites. Every website can be assigned a unique list of true and falses. This is what's known as a hash. When I say unique, it means that if anyone types the exact same letters, they'll get the exact same hash function back. There's a lot on the internet about how to create a hash that's really good. Just to give you just a general idea of one, imagine that we thought of every letter as a digit, some number. For example, we could just count off our alphabet or use an encoding like Unicode or ASCII. Once we've turned each character into a number, we can add up all those numbers in binary and take the last 5 binary digits or bits. Treating those as true and false, it gives us a somewhat random looking sequence, but one that we could reproduce from those letters. However we create the hash function, we now have a sequence which has something to do with the original name of the website. What we'd like to do is update our filter to know about this bad website. So what we do is we use our logical operator OR. Each component gets ORed together. So we could say false or false, that's false. True or false is true. True or false is another true. False with a false is false. And true with a false is true. We have now stored some of the information about Ruin My PC inside of this filter. But it won't be just one bad website. We'll also encounter other bad websites. Here's rotmyapple.net. It was determined by our security company. It too is a malicious website. So it also gets a hash function associated to it. In this case, I'll assume it's this one. I have assigned it a hash value of true, false, false, true. I now need to update my filter one more time. Remember, I update my filters with an OR. I now take true or false to get true. True or false to get true. True or false to get true. False or false to keep false. True or true to get true. I now see the resulting filter as a combination of the 2 different malicious websites. Over time, I'll keep filling in many different choices. Now, that's the way I store data into the filter, but I still lack a membership test. So now I claim that I've stored some information about negative websites into a filter. But how do I get information out? After all, we're after a membership test. Let's go to our web browser and type in rotmyapple. The web browser has inside of it the same program that computed the hash in the first place. And the guarantee of a hash is that it'll produce the same sequence of true and falses every single time. So, without doing much work, it can come up with that sequence. I've copied that hash value down here. It's the same one that our security firm came up with when it first decided that that was a negative website. Now, inside of my browser, I've stored the permanent filter. This updated filter has many, many websites, thousands, maybe millions. To get that information out, what it would mean is that I've seen this website before. That is, I've seen this sequence of trues and falses. Remember, we combined these as or. That meant it was in there or somebody else put it in there. Therefore, if we do an AND of our hash function with the filter, we should get back a true for every place that it was true originally. True and true gives us true. True and false gives us false. True and false gives us false. False and false gives us false. True and true gives us true. Notice that the resulting list is a perfect match to our hash. Notice we have a guarantee in this model. If we added this particular sequence to our list, then the ORs will turn every place that this was true into a true. Therefore, when we take an AND with that hash, it is guaranteed to be true at exactly the same places. That is, if we've seen the negative website before, then we have a formula for membership. So here's the logic of the Bloom test. If our website was one of our initial bad lists, then when we create the hash future time on some other new browser and AND it with our filter, it'll come back exactly as the hash we started with. That's a guarantee. So let's make this our membership test. We take the hash, we AND it with our filter, and we check if it comes back as the hash. What are we in danger of doing? Notice this is only a one-way test of membership. If we did find that this was previously known to be a bad web page, then this will detect it. The downside is it doesn't rule out the possibility that there could be a fluke in which a new hash comes in, unrelated to a bad website, and just happens to come back as its own hash, and therefore looks like a bad website, but it might not be. Let's see how that could happen. Suppose that at badboss.com is just a hangout for people to complain about people that they don't like working with. Let's assume that the hash function for this one came back as true, true, false, false. There's nothing negative with this website. But now let's see what the browser may tell us if it runs this test. By typing in this web page, it triggers the browser to compute the hash, which we copy from here. Notice we didn't update the filter because this was not a negative website. Nevertheless, see what happens when we run the filter test. True with true is true. True with true is true. True with true is true. False with false is false. True with false is false. We see that it's a perfect match. In this case, our test just got passed. What the browser will now do is trigger a warning, because this is a situation where the hash of badboss.com and with the filter turned out to equal the hash. This is what's known as a false positive. We have detected a web page which is perfectly fine, but warned the user that it could be malicious. Probably this is the right thing to do. Better to be safe than sorry. Let's write down the logic that models that kind of membership. What we see now is that it's not necessary that the web pages that we find in the bad list are bad, but it's possible. The symbols for that in logic are a diamond. This is the logic way to describe the membership that we've just created through this test. It is possible that this web page is an element of the bad websites. We can't be certain, but there are worlds in which it could have been a bad website. But in this case, it was a false positive. So what happens on the flip side? What if the hash with the filter doesn't equal the hash? Well, then we're guaranteed that we've never seen that web page on any malicious site before. We can say it is necessary. So to summarize, here's what our test can do. In a situation where we have a bad website, the hash and the filter will become the same as the hash. In that case, we know that it's a bad website to start with. But there can be false positives. There can be scenarios where the hash function of a good web page turns out to live inside the filter. And so we can have a scenario where the hash and the filter comes back as the hash and it wasn't on the naughty list. This means that the right logic to say here is that it's possible that the web is in the bad pages. That diamond stands for possible. There's a flip side to this. Suppose we take a test, we run the hash, and we end it with the filter, and it's not equal to the hash. In that case, we're guaranteed that we've never seen that web page on a negative list before. So we can be certain about that, and we add that. So we say that it's a necessary condition that the web page isn't bad. As we explore many other types of membership, we'll discover that it's helpful to have a more nuanced version of membership than just true or false. Maybe what we need to do is be circumspect and say, it's possibly true, it's necessarily false, or some flipped version of that. There are many other types of data structures that have been conjured over the years to explore membership in all the subtle ways that it occurs. Sometimes the goal is to speed up or narrow the time it would take to compute this. Other times we simply won't know because we don't have enough evidence. Each one follows a type of logic appropriate for the scenario you're in, but it will absolutely affect the set theory because what it means to be a member has changed from one application to the next. Be mindful when talking across disciplines to explore what kind of membership individuals are talking about. It comes with a logic, and with different logics, you get different expectations. Until next time. That's how you take care of your chalkboard.